Hi, I'm Jakub from DB Booster Academy. Here is a surprising fact. Most people who create indexes don't actually understand how and why they work. If you ask them, they usually say, well, indexes make queries faster. But that's not really an explanation. That's just the result, and sometimes not even true, as we'll see. And that's why so many developers create indexes by trial and error. In this video, I'll explain why indexes really work, when they help, and also when they don't. Once you understand the actual mechanics, you'll be able to design better indexes and do it faster. Index behavior isn't identical across all databases. Oracle, SQL Server, PostgreSQL, MySQL, they all have their differences. But the core principles of B3 indexes are the same. And that's actually what we'll focus on today. We will cover indexes from the ground up, how data are stored on disk, how B3 index is structured, how searches work inside it. We also look at when indexes help, when they don't, and clear up a few common myths along the way. That's the key to understanding why indexes can transform a slow query into a fast one, or sometimes make it even worse. First of all, let's start with how databases store data on disk. By disk, I mean any kind of storage. It could be a disk array, SSD, or something else. Not surprisingly, databases store data in files. However, these files are divided into small pieces of a fixed size. We call these pieces pages or blocks, and the exact size depends on the database engine. I'll use pages of 8 kilobytes as it is a very popular size. So in the end, we have one or more files, each divided into pages, and every page always belongs to exactly one database object, for example, a table or an index. Now let me introduce my table. It contains movies. The columns are ID as the primary key, movie name, country of origin, score as voted by people from the 0 for the worst movie to the 100 for the best one, language, status, budget, revenue, release date, and finally a description. I didn't include the description column in the slide because it's quite a big. The default storage for a database table is a heap. A heap organized table has no built-in order. The rows are simply stored as they arrive. Let's check the example. The green rows happen to land into page 0. The purple ones in page 1 and the green ones into page 2. There is no sorting, no pattern. Just whichever page has enough room. The number of rows that fit into a page also vary. Some rows are short, some are longer, and for example, the description column can make a big difference in size. The key idea is simple. The database just keeps filling pages with rows until they fit. The result is a collection of pages that together hold our entire table, but without any guaranteed order. In my case, I need 491 pages to store my movies table. The important question is, what if I need to search for a specific value? Let's say I want to find movies with the name Shockwave. But remember, a heap table has no order. So where do I begin? Page 0. First, I need to read the page into memory. We call this part cache. It's the place where we store the pages read from disk. When the page is in cache, I'll check row by row, scanning each name carefully. Finally, I find shockwave. Great, I can return that row, but my job isn't done. I have to finish scanning the rest of the rows on page 0. Next, I have to read page 1, again into memory, and scan every row. Then page 2, page 3, page after page, row after row, 4, 5, 6, and it just keeps going until at last I reach page 491, the very last page of my table. Only then I do know for sure that I found every copy of Shockwave. And that's the cost of searching in a heap. One long, exhausting journey through every single page. I had to read 491 pages and scan every single one of the 10,143 rows. However, 10,000 rows is nothing. That's actually a really small table. But now imagine I am dealing with hundreds of millions of rows spread across millions of pages. The effort of scanning through all of that would be extreme. By the way, when I introduce this concept live, someone usually asks, but what if the name is unique? Can't the database just stop? First, most tables have very few unique values. And second, without an index, the database has to scan all the pages. I'll show you why a bit later. So stay tuned. Before we move on to indexes, there is one more thing you really need to understand. A page is the unit of I/O. I/O stands for input and output, and in database world, it simply means reads and writes. There is no such thing as read one row or write one row. Whenever the database works with data, it always reads all or writes the entire page. In my case, that's 8 kilobyte. So when I read from disk, I don't get just one row. I have to pull the full 8 kilobyte page into memory, and in memory the page stays as it is, 8 kilobytes in size. If I change just a single row inside the page, or delete one, or insert a new one, when it's written back to disk, the database still has to write the entire 8 kilobyte page. That's how pages work, and it's the reason why minimizing the number of pages you touch is so important for performance. Let's go back to the search. A heap table full scan can be useful, and we'll come back to it later. But it's clear we need a more efficient way to find values with limited occurrences. And that's where a database object called B-tree index comes in. Strictly speaking, it's actually a B plus tree, but everyone just calls it B-tree. What matters is not the name, but how it works. Just like heap tables, the index is built from the same 8 kilobyte pages. Because it's a tree structure, it starts with a single page at the top, the root. This page is always well known because it's the entry point into the rest of the index. The root contains pointers to the next level, which may include one or many intermediate levels. Each page in an intermediate level points further down until we eventually reach the leaf page. A leaf page has no children. Instead, each leaf knows about its neighbor. The leaf level is connected through a doubly linked list, so we can move forward or backward across the leaves. In this example, we have 3 levels. at the very top, level 1, the root. Below that, level 2, the intermediate level. And finally, level 3, the leaves. Because we have three levels, we say the height of the tree is 3. Now here is something important. A B-tree index is always self-balancing. No matter which path you take from the root, you always walk through the same number of steps before you reach a leaf. Or simply put, all the leaves live on the same level, which is the level 3 in our case. Let's jump into an example and see how we can actually use this B-tree index to do a search. This example of an index covering the columns language and score, both ordered in ascending order. The index is essentially a copy of our data, so by creating it, we also increase the footprint on disk. Our table stays intact, just as it was before. In this example, we see another key feature of the index. The leaves contain the key values and one extra value called the row ID, which I will explain soon. However, point is that the key values are ordered in the leaves, first by language, and when the language is the same, then by score. For example, on this page, with all values for language Arabic, they are ordered by score 6, 10, 53, 99. Then there is a pointer, and because I have only 4 movies in Arabic, the next values are Basque 11 and Bengali 25, Bengali 95, and so on. You can also see that the highest values of each leaf page is stored in the intermediate page. And this entry points to it. This guarantees that when I use this pointer, all values in the leaf are the same or smaller than this value. And the same logic applies to the root and its pointers to intermediate levels. There is also an extra pointer not tied to any specific value, which handles everything greater than the highest value in the page. In short, the root and intermediate pages are used to navigate through the tree, while the leaves contain actual sorted key values. So let's make our first search. We are looking for rows with language Chinese and score 4. We know the root page, so we read it and check the entries with their values. We are looking for the first entry where our value is lower or equal. The value is Chinese 4, and Chinese 4 is greater than Cantonese 91. So we move to the next entry. Now Chinese 4 is less than the Chinese 98. The language is same, and the score 4 is lower than 98. So we follow this pointer to intermediate level page. Again, we compare our value against the entries. This time, the very first entry is equal, so we follow its pointer to the leaf. We check the key values, and in the leaf, we check the key values one by one. Chinese 1 is not equal. Chinese 3 is not equal. Chinese 4 matches, so we have a hit. But we are not finished yet. Since the index is not unique, there could be multiple rows with the same language and score. So we check the next value, Chinese 9 is not equal, so now we are done. In this search, we only had to read 3 pages, the root, 1 intermediate, and 1 leaf. That's it. Compare that with scanning 491 pages before. Huge difference. And the beauty is, reaching the first matching value or confirming the value does not exist at all always takes only as many as reads as the height of the tree. If there are more matching rows, the database simply keeps scanning forward in the leaves, so the number of read pages can be higher. This example of B3 is the classic one. You'll find in books, but it also comes with a very common flaw. In my example, there are only 3 to 5 index entries per page. That's fine for illustration, but it's not how things look in real life. So let's move to more realistic numbers. For column language, which is character-based value with an average, let's say, 8 characters, and score, which is an integer of 4 bytes, it's fair to assume that the root wouldn't hold just 3 to 5 entries. Instead, it could easily hold around 200. So the root can hold about 200 pointers. Each pointer leads to an intermediate level. It means we have 200 intermediate pages. Each of those can hold another 200 pointers. That makes about 40,000 leaves. Each leaf can store about 200 values. So together, the index covers roughly 8 million rows. 8 million rows. And the tree is still only 3 levels high. And here is the key point. To find a value, we don't scan millions of rows. We need just 3 I/O operations. One for the root, one for the intermediate, the one for the leaf. That's the brilliance of B-trees. Logarithmic power. 3 steps instead of scanning all the table pages. With an average of 200 entries per page, a tree of height 3 can cover roughly 8 million rows. If we increase the height to 4, it jumps to about 1.6 billion rows. Pretty awesome, isn't it? Of course, the actual number of entries per page depends on the length and number of the index columns. For example, if I create an index on a string that averages 50 characters, the index will be larger and fewer entries will fit on each page. It's also worth noting that different database engines apply techniques to keep indexes smaller. Things like compression, deduplication, and other optimizations. Maybe you are wondering, what's the index height in real life? This example comes from a production database, about 4 terabytes in size. Many indexes have a height of 1. Those are for small or empty tables. Most indexes are height 2 or 3. There are 327 indexes with height 4. Only 3 indexes reach height 5. And just one single index, height 6. So when in a multiple terabyte system, almost everything fits within 3 to 4 levels. Checking the timer. I am glad I didn't set a strict time limit for this video. Some topics just take time to master. I'd much rather go through it slowly and clearly than rush and miss the important parts. Let me know in the comments if you prefer this slower, detailed pace, or if you'd like me to make shorter more focused videos in the future. Thank you. Now it's time to explain the ROWID. Since our index contains only 2 columns, there's a good chance we'll need additional columns to satisfy the search query. Let's say I run the classic select star query. In this case, I need to return all the rows, all the columns, not just the language and score stored inside the index. That's where the ROWID comes in. As you already know, the index doesn't hold the full row. It stores the index key values and alongside them a pointer, here, ROWID, which leads back to the table where the rest of the columns are stored. The exact implementation of ROWID differs between database engines, but the key idea is always the same. In my case, the ROWID encodes file number in the database, the page number within that file, and the row number on that page. For example, in this leaf, the first index row points to the file 1, page 13, row 0. The second index row points to the file 1, page 58, row 1. The next points to file 1, page 120, row 3. And another pointer points to file 1, page 58, row 3. Accessing rows via ROWID means reading the corresponding table page, so each lookup adds an extra IO operation. Reading the full row for the value Chinese 4 takes me 4 IO operations. 3 to walk down the tree, and 1 more to access the table. The important point is this. Even if the index entries are right next to each other, their ROWID pointers can lead to a completely different table pages. That means if I have a bad luck, I may need an extra IO for every single index key that matches my criteria. If the query can be fully satisfied by the columns included in the index, then accessing the table is not necessary. We call these covering indexes because the index alone covers the entire query. Now, I do want to keep this video general and engine agnostic, but I have to make a note. In PostgreSQL, you may still need access the table even with a covering index because of how MVCC works there. I'll dive deeper into MVCC in another video, so if that sounds interesting, stick around and hit subscribe so you don't miss it. Let's take another example. Imagine I search for all rows where the language is English. In my table, that's more than 70% of all rows. To do this search, I would dive into the first key with the value English. As you already know, this operation costs as many IO operations as the height of the index. Then I'd have to read all the following rows with the same value, which means about 70% of my leaf index keys. Now, if this query can be answered by a covering index, it might still be faster because the index is smaller than the table. In my case, it only has 2 columns. But that depends heavily on the database engine. For a select star query, however, where I need go back to the table for other columns, I'll end up touching most of the table pages anyway. In that case, index access plus a table access is very likely slower than just doing a full table scan. The key point is simple. An index is only useful when it fulfills your tuning goals and when it's actually used. Common tuning goals are making queries faster or reducing resources consumption. Whether index access is better depends on the engine, because even full scans have optimizations like multi-block reads. Performance tuning is often about reducing the amount of work the database has to do. The threshold where the optimizer switches from index access to a full scan isn't based on some fixed percentage of rows. Instead, the optimizer decides before execution using statistics that describe your data. If those statistics are inaccurate, the optimizer might avoid an index even when it would be faster. That's why rules like if more than 10% of rows are selected, the engine will always do a full scans are myths. Why? Because, for example, the same data can be stored on a very different number of pages, depending on index fullness and row density. It's about much more than just the percentage of rows you need. Other factors, such as parameter settings and database configuration, play a big role as well. So instead of searching for this mythical threshold, the so-called holy grail of access paths, you should be familiar with the database engine you use, because each one behaves differently. Understand how much of your data you actually need and whether the index can cover it. In other words, can you avoid going back to the table? And finally, remember that a full table scan usually means reading every table page, but it can be faster sometimes and better option. There are a few exceptions as always, like queries with a limit clause, but those deserve a separate video. So this was the index search. Index can be useful for other scenarios, which I won't cover today, like constraints, unique and primary key, or order by clause, of course, joins, group by operations. And again, I plan to cover those topics in a separate video. I know I'm making promises like a politician before elections, but I'll do my best to keep them. Of course, the more subscribers I see, the more motivation I have to make this the next ones. But no pressure. Just kidding. Honestly, I'll be glad even if this video helps just one single person. As you can see, indexes are a broad topic. And even though this video has already been a bit longer, I haven't touched on the price of indexes. As my teacher Jim Rohn used to say, nothing in life is free. You either pay with hard work or with regrets. Indexes are no exception. They come with a cost. That will be the focus of my next video. So, I think we can wrap it up with a short summary and then we are done. Honestly, I feel like I even covered a little more than I planned. Oh wait, I nearly forgot. I promised you the story about full table scans, unique values, and whether the scan can stop early. Let's quickly go through it. Point 1. To let the database know that a value is unique, you must define a unique constraint. Point 2. When you define a unique constraint, the database will either reuse an existing index or create a new one, because an index is required to enforce uniqueness. Point 3. With an index in place, if you query for a specific value, the database can find it or confirm it's not there with just a number of IO operations equal to the height of the index tree. And this was the topic of today's video, the brilliance and the key idea behind indexes. That's why in practice the database will choose the index lookup instead of scanning the whole table. The takeaway from this is uniqueness of a value does not stop the full scan. The database needs an index and should use the index instead. However, I want to make one quick note here. Technically, a full scan can be interrupted in special cases. A good example is the limit clause, as mentioned before, but there are some catches, so I'll prepare a slide or two and explain the limit scenario in a future video. Now jump to the summary. Tables and pages. Point 1. Databases store their data in fixed-sized pages. Pages are the smallest thing the database can read or write. There is no such thing as reading just a single row. In a heap organized table, if I need to search for a value, I have to scan all the pages, and that can mean a lot of work. That's why we use indexes, another copy of our data that gives us a faster way to search sometimes. With an index, finding the first matching value only costs as many IOs as the height of the tree. And the good news is, in real systems, the tree height is usually very low, often just 3 or 4. It grows very slowly compared to the amount of data. But sometimes the index alone isn't enough. You may need to go back to the table, and that means more reads. Even with an index, you can still end up reading a large portion of your data. There are cases when a full table scan can actually be faster. And that's it for today. A beautiful session. Thanks for watching. I'd love your comments, feedback, or even ideas for topics you'd like me to cover. And if you enjoyed this, don't forget to like and subscribe. Take care and see you in the next one.